All right, welcome to this pre-lab video on lab E16, titration curves. So just one little note here. This is a break from our tradition. We have usually done both of the labs for that week in one pre-lab video. However, the two labs for this week do not cover the same concept. So it makes more sense for us to actually split them up. And the pre-lab video for the virtual lab this week will probably be broken into two parts because the things that you need for the calculations in the post-lab are different kinds of calculations than what you need for the pre-lab. So I will publish a pair of videos about that one at a later time. But let's get into this particular experiment. So for titration curves, this is lab E16. What we are getting into are titrations. Now, you are very familiar with titrations at this point. You did them all through Gen Chem 1, all through Gen Chem 1 lab, and we just started to see a little bit of them in Gen Chem 2, in especially the lab that we just did on the thermodynamics of acid dissociation. Now, where this is different is instead of using the titration just as a means to calculate concentration, we're going to do something a little bit more similar to what we did in the thermodynamics of dissociation lab, where we are actually going to use it to find data about the acid itself. And the data that we are going to use comes as a result of something called a titration curve. A titration curve is a graph, and that graph plots the pH of the solution on the y-axis and the base added on the x. That is the primary purpose of this particular graph. And as you'll see, there are going to be different kinds of graphs that come about as a result of the different characteristics of the acid itself. So the most common type of titration, the acid-base titration, is one that we have seen many times before. It's where we have an acid in our flask and we are titrating base into that acid. So those are characterized by having very low pHs at the start because, well, the starting material is an acid, and regardless of concentration, acids are going to have pHs that are less than 7. And if it's of any kind of considerable concentration, 0.01 and above, it's going to have a relatively low pH as well. And as we add base through the point of the titration, we will see a gradual increase in pH until basically we hit that equivalence point and it's supposed to even out. Now, remember, equivalence point is simply the point where the moles of acid that were in the flask are equal to the moles of base that were added to the flask. And depending upon the nature of the acid, we're going to get equivalence points in one of two spots. If our acid is strong, like hydrochloric acid, that pH is going to be right at 7.00. And this has to do a lot with conjugate acid-base theory. The stronger the acid is, the weaker its conjugate is. And so by hydrochloric acid being so strong, the conjugate base, the chloride ion, is by so many terms weak. And it's so weak in effect that it really does nothing to water at all. It's a completely neutral ion. Whereas if we look at acetic acid, we see that not only do we have a higher starting pH here, our equivalence point's not at 7.00. Now you may wonder about this, but again, it comes back to conjugate acid-base theory. If acetic acid is a weak acid, that means that its conjugate base, the acetate ion, is a weak base. As a weak base, it is going to act like a base when it's by itself in water. And at the equivalence point, all of the H pluses and OH minuses are gone. We've got a solution of sodium acetate sitting there. The sodium ion has nothing to do with water. It is as neutral as it comes. And so the acetate's there by itself, and it's going to start grabbing protons off of water molecules to satisfy its basic nature. And that is going to leave those little bits of hydroxide behind to raise the pH up to a basic level. Not so terribly basic, 8.73 in this particular case, but basic enough to notice that if you dipped a pH strip in there, you would notice that it's basic. So there are some differences, and titration curves can give us some of that information. So when we look at titration curves, they come in two different kinds, two different varieties. There are the strong acid, strong base curves. These are the ones that we have dealt with the most often. Hydrochloric acid reacts with sodium hydroxide. Sulfuric acid reacts with sodium hydroxide, potassium hydroxide, whatever the case is. What's notable about them is because they are strong acids, their initial pH is low. And because of that strong character, you saw this in the pH and acid dilution last week. It takes a good bit of dilution to get that pH to go toward neutral. So what we see is a very, 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 very gradual increase in pH as the acid is neutralized, to the point that we're going to see this very flat, just slightly curving upward kind of trend until we get that near that equivalence point. And at the equivalence point, things change very, very quickly. Our remaining amount of hydrogen ion is relatively small. Our remaining amount of hydroxide is, well, again, close to nothing, but we're adding a greater proportion of hydroxide relative to the amount of H plus that is left. And that is going to cause that pH to spike dramatically. And that's kind of what we call the rapid rise region in the curve. It is going to go up considerably in very, very little amounts of base. And then after the equivalence point, the pH kind of levels off as we start to hit those higher levels. And again, if you think about that simulation that you did last week with the pH and the dilution, you saw that, right? Adding additional hydroxide isn't going to make that big of a difference, because once we hit that top level, it's really kind of hard with all of the dilution that's taken place to do much more than we've already done. So this is an example of a strong acid, strong base curve. And you can see in this strong acid, strong base curve, we've got the low starting pH. We've got this rapid rise region that is we've got this region initially that is very flat. It takes 10, 20, 30, 40 milliliters to go from pH 1 to pH 2. And then finally, we have the rapid rise region here, where in a matter of about 5 milliliters, we go from pH 2 to pH 12. And then once again, it levels off again once we get into that base zone. And if this graph had continued, we would see a very, very, very gradual increase in pH. The other kind of titration is a weak, strong titration. Weak acid in the flask, strong base in the burette. And from that standpoint, there are some noticeable differences. This is the kind of thing that we see when we do acetic acid in sodium hydroxide. First of all, because the acid is weaker, that starting pH is likely to be higher. Now, we're not talking higher like pH 4 or pH 5, but instead of pH 1, maybe it's at pH 2.5 or pH 3. The second thing, we already talked about this, the equivalence point. The equivalence point is actually going to be in the basic zone. It's going to be greater than 7. because you've got that conjugate base all by itself, and that conjugate base is going to start picking protons off of water to satisfy its basic nature. Now, the other important thing, and this is something that we utilized in that thermodynamics of a dissociation lab, is the half-equivalence point. So if I take that volume, it takes me 20 milliliters, for example, to go from start of titration to equivalence point. At half of that volume, so 10 milliliters, what we get is something called the half equivalence point. And at the half equivalence point, the pH of the solution is equal to the pKa of that acid. Why that is particularly useful, again, going back to the calculations that you did with pH being equal to pKa, the measured pH is equal to the negative log of the Ka for the acid. Doing some manipulating algebraically, we can determine the value of the Ka for our acid by taking the antilog of the negative pH that we measure at the half equivalence point. Now, where this is a particular note for us is helping us to identify unknown acids. Since each acid has a specific value for its Ka, and they tend to be different from each other, this can at least give us some clues as to what weak acid we are ultimately dealing with. And again, we used this in that thermodynamics of dissociation lab. We ended up applying that to figure out the free energy of dissociation, but it has other applications as well. So again, let's look at the differences here. So again, highlighting our starting point. This starting point here looks to be about pH 2.7 or so. Notice that this part of the curve is different. In fact, I really can't do it with a straight circle. I'm going to have to freeform it here. And the main reason for this is that this particular region is not just any old kind of reaction system. This is a buffer system. And we'll talk, you'll hear more about buffers in the other two videos. But buffers are where we have this unique combination of acid and conjugate base present at the same time, and they have a resistance to pH change, but in a different way than what we saw in the strong acid, strong base. Because of this buffer system, we can see that our rapid rise region is considerably lesser. Notice that in the span of about 45 to 55, so a 10 milliliter span, we went from pH 6 to pH 12. Again, remember, in 5 milliliters, we did a difference of 10 pH points in the strong acid. In 10 milliliters here, we did a change of 6. So because that region has shrunk, we can see that it overall is going to shrink the rapid rise region as well. And then finally, the region here is pretty much the same. We do see that it's sloped a little bit higher, again, potentially because of some buffering that's going on. But overall, it levels off relatively quickly because, again, same reason. The hydroxides that are being shown there in excess, well, they're already pretty diluted to a degree. It's going to be difficult for the pH to really change drastically in that region. So again, the key differences: pH, starting pH for the weak acid is higher than the starting pH for the strong acid. The second region, region 2, the buffer region for the weak acid is not seen in the strong acid. Strong acid stays relatively flat until we get to the equivalence point. The weak acid curves upward as we go through that buffering region. The equivalence point itself in the strong acid is large. In the weak acid, it is smaller. And then lastly, the pH for the strong acid is right around 7. The pH for the weak acid is always above 7. The important thing to note is that the weaker the acid is, the more prominent these differences are going to be. Now, one last point about this particular lab, you're going to do 3 titration curves in total. You're going to do strong acid, strong base. You're going to do weak acid, strong base. And you are going to do polyprotic acid, strong base. The polyprotic acid that we will look at is the phosphoric acid. And while there are 3 hydrogens, only 2 of them are really acidic in that kind of sense. So what we will see is a double dose here, 2 equivalence points. And you will use that data to figure out the Ka values for the 2 equivalence points for phosphoric acid. Notice again, with this being a weak acid, so this is phosphorus acid, HPO3, but the properties, the characteristics are relatively similar. The stronger acid is always the first deprotonation. So you can see we have a relatively low starting pH. This is a buffering region here, although it is not changing as considerably as we saw in the previous example. And we end up getting a first equivalence point in the acidic region. And the reason for that is this conjugate here does have weak base properties, but it's amphiprotic. It has weak acid properties as well. The weak acid properties actually dominate the weak base properties, so that gives us the acidic pH that we're talking about here. It goes through its equivalence point, and you'll see that its rapid rise region here has a more definitive positive slope than the first one did, because it is a weaker acid than the first. And as a result, that pH of that second equivalence point is definitively more basic. So those are the 3 types of curves that you're going to investigate in this lab. Walking on over to the pre-lab. For the pre-lab assignment here, you are asked to investigate in question 1 here, what is the pKa of the acid? Well, again, this is the half equivalence point. So if the equivalence point is at 10 milliliters, you are going to look at 5 milliliters and determine, and actually all it's asking for is at what point. So the correct answer there is the half equivalence point. It's not asking you actually what the pKa is. We could investigate and estimate that that is pretty close to pH 5, maybe just a little bit below. Question here, what kind of titration curve is this? Based upon the information I just gave you, you should be able to answer that relatively easily, given the very unique kind of character of the reaction itself, the low starting pH, the shape of the curve itself. Number 3, neutral at the equivalence point, already talked about that. Identify the dominant species that determine the pH for the titration of a monoprotic acid, and write the relevant equation that produces this. So we know that based upon our data at the beginning, the pH is going to be acidic. So we need to identify the particle, the weak acid, we'll just call it HA, that produces that pH. Halfway to the equivalence point, we know that pH is equal to pKa, but it's still acidic. So we know what the dominant species is there. At the equivalence point, the pH is going to be basic. And so that, again, is where the conjugate base is taking over. And then past the equivalence point, we have excess NaOH, which means that this is going to be basic. And the basic nature is just from the sodium hydroxide, leaving behind all these extra hydroxides. So once we get past the equivalence point, that conjugate base doesn't really have that big of an impact on the pH. That concentration of excess hydroxide is the primary dominating factor to give us the hydroxide. And then for the last one here, this is just your friendly old titration equation, where we've got MA times VA over NA equal to the molarity of the base times the volume of the base over the stoichiometric coefficient of the base. You've probably done this kind of equation at least a dozen, if not more times. Just make sure that you've got your balanced chemical equation beforehand so that you can get those values of N. Remember, the A's stand for the acid, which would be the hydrochloric acid. The B's stand for base, which would be the sodium hydroxide. And so as far as this is concerned, that's all that we need for this particular pre-lab assignment. If you have any questions, feel free to reach out to me. There's lots of other goodies here in the lab itself, but those will be addressed on lab day, including this little gem right here, the extra credit assignment, which is all about the same kind of stuff that we were talking about. Only in this case, I've got a titration curve here, and I don't know what the acid is. So going and grabbing the necessary data off of this graph to answer these questions can earn you up to 10 bonus points, which are always needed and always appreciated. So I'm going to close the video out for now, but until I see you, good luck with the pre-lab, and I will see you in lab.